This lecture continues consideration of the heart physiology, and now we are going to study cardiac cycle and investigation methods of the heart functioning. The first part of lecture considers cardiac cycle. Cardiac cycle is the sequence of events that repetitively occur during heart functioning. These events include many changes, including the state of the heart muscle, the state of valves, changes of ventricular pressure, of ventricular volume, and the sounds that appear during the heart functioning. But before we go deeper into consideration of all phases of cardiac cycle, first let's make a simple division of the cardiac cycle into two basic parts, the systole and diastole. Duration of the cardiac cycle, and as well both systole and diastole, is variable, and values of time are given here for general idea of ratio between these parts of cycle, and for general resting values, approximately average values of the cardiac cycle. They are calculated for the standard heart rate, about 75 beats per minute, when cardiac cycle lasts for 0.8 of a second. In this case, systole lasts approximately about 0.3, or more exactly, they say 0.33 seconds. And diastole about 0.87 seconds. So in a resting state, the heart has enough time for the rest after the contraction. Let's make the simplest scheme that shows the ratio between these parts of the atrial and ventricular contraction. This will be two timelines for the contraction of the atria and ventricles. The whole duration of this timeline, let it be 0.8 of a second. Then we divide these lines into 8 equal parts so that each portion lasts for 0.1 second. And atrial contraction that occurs first when impulse is generated in the sinus node and conducted firstly through the atria, produces contraction of atria that lasts about 0.1 second. After this, contraction of ventricles begin. You remember that it's due to this sequence is due to the atrioventricular delay, because conduction of excitation through atria is rather quick, about 1 meter per second, and only slowing down in the atrioventricular node to a few centimeters per second gives opportunity for atria to finish its contraction, and only then ventricles begin their contraction, which lasts for slightly over 0.3 of a second, and total duration will be 0.33. Then there starts the total pause, general pause for the both atria and ventricle. They have no contraction, they are in resting state. And after this, atria again start to contract and cycle becomes repeated, while at the same time ventricles during the atrial contraction or atrial systole still are in their resting state. And just after this, they begin their contraction again. So you may see that the whole duration of the systole is slightly above 0.3 of second, 0.33, and duration of the diastole is 0.47, and so the total duration of the cardiac cycle in this case makes the standard value of 0.8 of a second. So this is very simple scheme. It's just the first primitive division of the cardiac cycle, but this is the basis which should be well understood. Now we come to the more detailed consideration, still not in full difficult or complexity, but it's important and shows the physics of the operation of the ventricles. Because you see here the diagram is called the volume pressure for single cardiac cycle, and this refers to left ventricle. You see, the left ventricular volume is on the horizontal axis, while the left intraventricular pressure values are shown on the vertical axis. The volume and pressure are related to each other, and in the closed system they are inversely proportionally related. The heart becomes the closed system, the ventricle, when valves become closed. But anyway, the there is interaction between the volume and pressure. Let's begin consideration from the point B. Now we start from the systole of the ventricles. And this moment shows when mitral valve closes. And generally the cardiac cycle begins from systole, and they say that this is moment when mitral valve closes. To be exactly true, there is a smallest negligible period before closure. The ventricles begin their contraction practically from zero level of millimeter mercury, and it's enough to reach just a few to overcome the pressure of the atria, and so in this case mitral valve become closed. Actually it's almost closed before contraction, because the cusps of the valve are floating on the surface of blood, and blood fills entire ventricle, and end diastolic volume, you may see here, it's about 120, more or less standard value. This end diastolic volume keeps the valve cusps floating, so they almost close. It's just enough to make a little pressure exceeding the atrial pressure to make it tightly closed. This moment is the mitral valve closure, and to be exact, it starts just a few hundredths of a second later after beginning of contraction, and so then mitral valves become closed. And now we have standard unchanged volume in the ventricles, because while mitral valve have already closed, the aortic valve is still closed after the diastole, because from the beginning of diastole they become closed already. So this is a moment when all valves are closed, the ventricle is filled with volume of blood, and blood, as any fluid, is not compressible. We cannot compress it, and ventricle try to do it. They contract, and this results in great and fast increase of pressure, while really volume cannot be changed, and volume remains the same. And that's why you see here you see isovolumetric process. Volume has not changed, but pressure goes upward, and pressure increases very quickly until the moment when aortic valve opens. All this pathway, vertical way from moment of closure of mitral valve until the opening of the aortic valve, the volume is unchanged. Therefore we say this is isovolumetric contraction. It's a short period because pressure in the closed system, in an attempt to decrease this volume, the pressure increases very quickly. When aortic valve opens, when pressure in the ventricle reaches the level of pressure behind the valve in aorta and slightly exceeds this, and you may see this is diastolic pressure level. This 80 millimeters mercury, diastolic pressure level, and actually it's necessary to create slightly above 81, but generally we can say it's enough to reach the pressure of diastolic, and then ventricles continue to contract and contract even stronger and create higher pressure, not only by 1 or 2 millimeters, but you see by pressure up to 120. But this is the period of ejection period, when ventricles continue to contract and eject the systolic volume of blood into aorta. And you see first the line goes upward, showing that pressure increases, but at the same time lies according to horizontal axis, volume comes to the lower value, and this value is about 50 milliliters. This is the end systolic volume, and pressure is reached up to systolic level, and volume remaining in the ventricle is the end systolic volume. So if it was 120 previously, now, for example, for standard values, 70 milliliters went into aorta, become ejected, and remaining volume composes the end systolic volume, about 50 milliliters for average. And now the ventricles begin their relaxation. When ventricles begin relaxation, immediately the blood pressure in aorta appears to be higher than in ventricles, because ventricular pressure decreases and blood starts to move back to the ventricle. And also, it's simplified now, and in reality there is very little negligible time between beginning of relaxation and backflow closure of the aortic valve by the backflow of blood. But they start from point D, point when aortic valve is closed already. So it's very little time, negligible. And so when aortic valve closes, again we have situation when all valves are closed. Pressure in the ventricle is just slightly less than systolic, therefore the valve between atria and ventricles will not open because atrial pressure is much less. And aortic valve is already closed. So while all valves are closed and volume of the blood is not changed, remains constant, the ventricles try to relax, to enlarge this volume, to increase it. And the attempt to increase volume greatly decreases pressure. And pressure falls practically to zero level. And again, it occurs without any changes of volume because it's fixed volume with closed valves. So this is the isovolumetric relaxation. And then when pressure becomes very low, and at the moment when it becomes less than in atria, immediately valves between atria and ventricles become open. And it's enough to reach almost zero, so because the pressure in the atria is very little. So practically it goes all practically to zero, and then opening of valves, mitral valve occur, and so it begins the filling. And you see process of filling goes practically without changes of pressure. And just in the end we have slight change of pressure. You see this arrow slightly makes a turn, and this is because the contraction of atria, the last moment in the filling of the ventricle. So according to this figure you can notice that there are 4 at least processes that occur during cycle, and they make 2 pairs. One pair is 2 isovolumetric periods, isovolumetric contraction and isovolumetric relaxation, and 2 opposite periods of ejection and filling. Blood goes out of ventricle during ejection, but comes to the ventricle just from the atria, of course, during filling. And so 4 phases we can observe at least. Plus this is atrial systole or atrial contraction, which makes its contribution not great, but 20%, 15% to the filling of the ventricle. So at least 5 parts we can differentiate, and 4 of them make pairs with opposite meaning. Isovolumetric contraction is the first half of systole, and ejection period is the second. Then isovolumetric relaxation occurs in the diastole beginning, and filling, which is opposite to ejection. So it's rather easy and logical to memorize and understand these processes. Now let's go deeper into the details. This is cardiac cycle with consideration of few at least changes. First, pressure in the left ventricle. You see it changes greatly during the cycle. Then the black line shows the volume of blood in the left ventricle, how it changes during the cardiac cycle. And the last line shows the first and second sounds of the heart, which appear due to valves functioning predominantly. So at least these events are described here in details. And here we can observe this 5 portion which we saw previously on this previous slide. This is systole with its 2 main parts. The period of isovolumetric contraction. You see the black line does not change here. This portion that is designated by number 1. No changes of volume. So this is isovolumetric contraction, and pressure goes upward very quickly. Then when we exceed the diastolic pressure, there occurs the ejection period of the systole, when blood goes out of ventricle, and it can be seen easily by the black line of volume that it goes downward. Blood volume decreases, but not totally, just for the systolic volume, and end systolic about 50 milliliters remain in the heart. And heart, even in case of high activity, high physical exercise level, never releases all the blood from the ventricle inside until the very last drop. It never happens. a little amount always remains. This ejection fraction never can reach 100%. Then, after ejection, diastole starts, and diastole starts from the isovolumetric contraction, where relaxation, when pressure decreases greatly with the same constant volume. The black line with number 3, you see no changes of volume, while the pressure, blue line, goes downward very quickly, drops down. Then opening of mitral valve enables ventricular filling, and filling begins after isovolumetric relaxation. Filling begins and goes for the most of diastole passively, and then there is under number 5 active filling due to atrial systole or atrial contraction. And atrial systole do not mix with simply systole because it's a part of the diastolic period of the heart. Number 5 in this picture. So again we consider the 5 pieces, and now we add division of ejection and filling into rapid and slowed down or reduced, and then you have classical cardiac cycle description. So let's begin this description with the 7 phases. Actually, in classifications that are present in many Russian textbooks, for example, we have classical consideration of 9 phases, with the mentioned before very short periods before closure of valves. Before beginning of isovolumetric phases, they add a little phase of contraction without still closure of valves, or relaxation with before closure of the aortic valve. But as most of textbooks simplified for 7 phases, we are going to consider exactly 7 phases of the cardiac cycle. Just you should understand that from the very beginning of contraction, immediate closure of valves, not instantly. Anyway, there are few pieces of millisecond occur. So, atrial systole, here is shown, you see the line slightly elevated pressure. Actually, it's a part of diastole, but let's see atrial systole because it's the beginning of the total contraction of the heart under impulses that come from the sinus node. So, and then systole begins. The systole first starts from the closure of the mitral valve. And when atrioventricular valves, both mitral and tricuspid, close, look at this moment, only from this moment pressure starts to go upward very quickly. And at this moment, the first sound, main component, begins. The first heart sound occurs in the beginning of a systole, so it's called a systolic. And it takes practically the whole next phase, which is the isovolumetric ventricular contraction, the next portion. You see the black line with volume that shows the volume under number 1. The red line now shows no changes of volume. Volume is constant, so it's isovolumetric ventricular contraction, but due to this constant fixed volume, the attempt to contract of the ventricle increases pressure very quickly. So pressure goes upward very quickly and reaches diastolic level very soon. So that isovolumetric ventricular contraction is a short period. And here we reach the level of the diastolic pressure in the aorta and exceed it slightly. So from this moment, the aortic valve is open. Ventricles continue their contraction, so force increases and pressure grows further. And this produces the rapid ventricular ejection. Really, it goes rapidly because ventricles still produce their contraction further and further. And most of the systolic volume is ejected during this rapid ventricular ejection. Then the force of contraction starts to decrease, and it's already called the reduced ventricular ejection. This is slower going with less pressure increase, and so, but still certain volume goes into aorta from ventricles. Then it's finished contraction and relaxation begins. And after this we have the diastole. And again, here I may remind you that from the beginning of relaxation until backflow of blood provides closure of semilunar valves, there is a very little negligible period. In Russian literature it's called proto-diastolic period. And not only in Russian, actually in the German physiology, many. But we consider 7 phases, so we know that it happens, the smallest piece of time that required for closure of semilunar valves. But we start this phase from exactly the valves closure. Semilunar valves close because blood turns back to the ventricles where pressure already decreases and fills the valve, and valves become closed, semilunar valves. So this moment, when red arrow shows this moment, corresponds to the beginning of the second heart sound. And as it lasts, it goes within the isovolumetric, just now relaxation period. This is second heart sound. Oscillation that occur during closure of semilunar valves. Actually, not valves themselves produce this sound, but mostly the oscillation of the whole walls of the heart. But valves also may give certain components. And this is the beginning closure of the semilunar valves at the beginning of the isovolumetric ventricular relaxation, short period when pressure drops down and volume is constant. And the number 4, you see a red line, shows that volume is constant, no changes. All valves are closed, both semilunar and atrioventricular. But attempt to relax and make larger volume in ventricles brings this quick drop of pressure, and pressure goes down very quickly and finally reaches almost zero level, so that pressure in ventricles becomes smaller, less than in atria, which opens atrioventricular valves and finishes the phase of isovolumetric ventricular relaxation and begins the rapid ventricular filling. Why it's rapid initially? Because during the closed state of atrioventricular valve, during the contraction of ventricles, blood continuously went to the left atrium from the pulmonary veins, and without stop it went into the atrium, and atrium by this moment accumulated certain amount of blood, which easily moves into relaxed ventricle and fills it rapidly at first. So this approximately, under number 5, you see this quick increase of volume, and so mostly filling occurs during this time. Then the current of blood flow becomes slower, because now blood only comes through pulmonary veins and nothing is accumulated. So blood flow becomes slower, and this is called reduced ventricular filling. So it's the numbered 6 on the figure of volume, black line. And then finally, again, we come back to the atrial systole, which is mentioned first. But now you see again additional filling occurs due to contraction of the atria, which adds some more blood, 15 to maybe 20 milliliters or 20% of the total end diastolic volume. So now it's ready to next cycle. So the seven phases we have considered, and I hope you have a general idea. It's necessary to remember the borders between the phases. For example, when isovolumetric ventricular contraction is over, when atrioventricular, semilunar valves open, this moves start the rapid ventricular ejection. Or, for example, when the phase of the isovolumetric ventricular relaxation is ended, when the atrioventricular valves become open and filling begins. So rapid ventricular filling and isovolumetric ventricular relaxation are divided by one event, by opening of atrioventricular valves for the left side of the heart. This is the mitral valve. And the borders between rapid and reduced processes, both ejection and filling, are not as greatly lined, so it's very approximately. But between isovolumetric periods and others, it's easy to find a moment when it starts and when it becomes ended. and it's necessary to understand it logically so that you don't have to memorize it simply mechanically. Now, let's consider again the pumping function of the right and left ventricles. It was considered in the previous lectures, so that I remind only values. Difference exists in the systolic and generally pressures of the both ventricles. Left ventricle develops the classical pressure characteristic for arterial values with average 120, and the right ventricle for the same systolic ejection volume produces pressure 15 to 30 millimeters with average about 25 millimeters mercury. So, and as a result, they both produce the same stroke volume and with the same ejection fraction. And classical stroke volume is considered to be about 70 milliliters. And ejection fraction, I remind you, this is very important in clinical practice index, and it's calculated as the ratio of the stroke volume ejected portion to the total end diastolic volume, and so it's ejection fraction taken in percentage. And you see above the values are full range of values from 50 to 75%, so at least half of volume should be ejected, but 50 is not the best index, of course. For average resting state, it should be about 55–60% of the total end diastolic volume. For physical activity, this percentage increases up to 90 and perhaps even up to 95, but not necessarily, depends on the on the level of training of the person. Then cardiac output calculation. It's not the first time we encounter this important index, cardiac output, but let's recall again. Volume of blood pumped by the heart per minute. And it can be calculated by multiplication of the two values. Volume that is ejected by left ventricle after one contraction is the stroke or systolic volume. And per minute, it depends on how many such contractions were performed. So, stroke volume is multiplied by the heart rate, number of contractions per minute. And then milliliters multiplied by beats per minute make milliliters per minute. 70 by 75, it's slightly over 5,000, but we can simplify it to round value of the 5 liters per minute. This is a classical resting level of the cardiac output. Of course, it depends on the person more or less, but for average person, it should be like this. This is a resting state, and when there are physical activities, there is state of physical activity, this value increases up to some number of times. We'll consider in future how many times it can be increased. Now, indices of myocardial contractility. First, what you should understand, what is contractility itself. It's greatly related to the force of contraction, but not only force is included into this index. Contractility means both force and velocity of contraction. It depends on both. So with the same force but faster contraction shows the higher contractility. The same force but slower contraction, it's less contractility. But both factors, force and velocity, are important. And there are few indices of the contractility, and most widely used is the ejection fraction. We already considered just a few slides before. From 50 to 70% normally, and no less than 50 in norm. So minimal level is half should be ejected from ventricle, but better more, and up to 75. But usually these limits are not often. 50 is not good for healthy person, 75 is not much usual. So basically it's between 55 to 60, or 60 sometimes, most often. This is a simple index, but this next one about it, and with ejection fraction is clear. Higher ejection fraction, the higher is contractility. It's a characteristic of contractility. And now we come to the next more difficult index of the myocardial contractility, velocity of the pressure increase during isovolumetric contraction. It's called dP per dt, which refers mostly to physics or mathematics, but simplified you can say delta P ratio to delta T. So how much pressure increases per each time unit. for each moment of time. See, this is a part of figure of pressure elevation in the left ventricle during isovolumetric contraction and partially during ejection fraction. So, and you see how it goes up, and highest increase occurs exactly during isovolumetric contraction, simply because of isovolumetric conditions. We already mentioned many times that fixed volume, unchanged constant volume, an attempt to decrease this volume produces great increase in pressure. So pressure becomes higher and higher after isovolumetric period, but it doesn't grow so quickly. So greatest elevation practically occurs exactly during isovolumetric contraction. So we assess the maximal velocity of pressure increase. And look, this is end of the isovolumetric contraction, when blood pressure in the ventricle reaches and slightly exceeds the pressure behind the valves. Of course, you should be aware that this is a standard case, 80, but particular person, individual, can have different diastolic pressure. And in this case, the end of isovolumetric contraction will not be by the moment when pressure reaches 80. No, any particular person diastolic pressure, this is the moment when this is the end of isovolumetric contraction. If someone has, for example, pressure 110, let's say, per 60, if the diastolic pressure is 60, so when ventricles reach the pressure 60 and slightly over, then the aortic valve becomes open and ejection begins. So for any individual values of the arterial blood pressure, the end of isovolumetric contraction and beginning of the ejection occurs when pressure in ventricles reaches the level, for simplifying we may say reaches, but really it should slightly exceed the pressure in the aorta, which is diastolic at the moment. It's not always set 80, that's why I again started to talk about it. But here it's classical 80 cross-section occurs and closure of valves is over and valve becomes open, semilunar aortic valve. You see now the increase in pressure, dP or delta P, is this value shown by the red arrow. And it occurs within the horizontal change of time, delta T, difference in time, during this time. So ratio of this elevation of pressure, which is achieved during this time period of isovolumetric contraction, delta T, is the index of the myocardial contractility. You see, it depends on both, and you may conclude that with higher difference of pressure achieved within this time, the contractility becomes higher, but also it can become higher without even changes of delta P, just by shortening the time interval. If isovolumetric contraction takes less time, so the same elevation of pressure is reached within shorter time period, so it also contributes to shows higher heart contractility, because dt is in denominator, so it creates higher value of this ratio. Practically, you may say that the angle, the degree of the angular degree under which this line of pressure goes upward shows the contractility, and the closer it's to vertical line, the higher is contractility, and greater declining of this line shows slower going upward, shows less myocardial contractility. And now we switch to the second part of the lecture. This is methods of the heart investigation. And heart investigation involves many different methods. Of course, first to be considered is the classical method, now the routine method of heart investigation, easily used, widespread. This is electrocardiography. ECG, electrocardiographic method, is one of the main used widespread, because it's well developed, well studied, and even if it's sometimes not exactly fully explained, but at least we know which conclusions we can make on the basis of changes of the ECG record. But then also we still consider that sounds of the heart, and phono say the sounds. So phonocardiography studies the sounds of the heart, including normal heart sound and different noises that appear, and they're called murmurs. Usually phonocardiography is not estimated alone separately from other records. Classically, it should be recorded in parallel synchronously with electrocardiography. In this case, two records, simultaneous records, provide much more information because relations can be established between two records. And for full estimation, also sometimes they include also the sphygmography, the pulse recording. And when these lines at least are recorded, electrocardiographic record, phonocardiographic, and sphygmogram, so it's called collectively the polycardiography. Polycardiography, many records considering the heart functioning from different sides. And finally, one more additional way of investigation of the heart, which gives us a lot of information and helps to visualize many heart features. This is echocardiography or ultrasound heart investigation. It provides estimation of some morphology in the heart, functional problem, and so on, and we'll consider closer to the end. Now we concentrate on electrocardiography and origin of ECG, electrocardiogram. This is a difference of potentials. You know, the heart regularly generates impulses, and these impulses are conducted along the conductive system of the heart and spread to the cardiomyocytes of contractile function. And so there appears the difference of potentials. This difference does not exist constantly. It appears, increases, decreases, sometimes disappears, but it can be recorded. Of course, in the heart itself, the potentials are much greater, and potentials that reach the surface of the skin are very little, and they require amplification, and that's why the devices that record ECG should be able to differentiate, to amplify this potential without great noise, this so-called noise. And generally, this all records appears due to rhythmical excitation of the heart. Potential differences arise between the excited and unexcited parts of the heart muscle. Look here, this is the moment when conduction starts to go downward the interventricular septum. So bundle of his is already excited, while the most part of the heart, including the apex and the walls of the ventricles, are not yet excited. You remember that resting excitable cell has negative potential inside and positive on the surface, but excited cells at the moment of excitation, which corresponds to the peak upper portion of potential, have negativity outside, while the inner side of the membrane becomes charged positive. So you see, if the surface becomes negative, it shows the excitation. And then, whereas you see in the interventricular septum minuses, it shows that this area of the heart is already excited, while positive charges on the surface correspond to negativity inside the cell, shows unexcited part of the cell. So this is excited septum, and this is unexcited myocardium. And between these two parts, difference of potential appears, and this difference changes while the cardiac cycle proceeds. And it can come to zero at a certain moment, but right now, at this very moment, there is a difference, and it's registered by the voltmeter. And the vector of conduction of excitation corresponds to this arrow that goes practically through the interventricular septum, from excited portion with minuses to the unexcited portion of the heart with positive charges on the surface. This is vector or axis, electrical axis of the heart at this moment. And you see points R, A, and B. And these points are points of where electrodes, for this example, are attached. And you see the voltmeter shows the potential difference between these 2 points. And potential difference is not zero, so it's a certain value, positive value. Actually, points A and B are approximate, but they approximately correspond to the measurement of the difference of potentials between the right hand and left hands. Practically this corresponds. So they appear the difference. First, I want to remind you that all this method was developed on the basis of works of this scientist, Wilhelm Einthoven. He started his work even before the 20th century started, but he suggested the method of registration of ECG first in 1903. So it was just the very beginning of the 20th century. And he worked hard to develop these devices which were extremely complex at the moment. It's very different from some simple apparatuses we use now, because it was not time for development of such devices, and it was not easy, and many difficulties he met during investigation and development of this method. Of course, finally we have very different method, but the basis of his work is great. You see, this is example of one version of the electrocardiographic recorder. He developed numerous different versions, but this was not the first, at least, and not the last. And you see here what we should do the tested person. The tested person submerges two hands and a left leg into salt solution in order to get good record of the ECG. Fortunately, now we don't have to do nothing like this, and it's easy, and we can monitor even on a daily basis this ECG with very little appliances, not like this with many kilograms. But only on basis of these works, the total method was developed. And he was the first who suggested the application of electrodes according to this scheme, which is still called the Einthoven's triangle. You see, right hand, left hand, and foot, left foot. And this triangle around the heart is important, and still we consider this triangle, and the next slide is going to show you again. And also he was the first who suggested the describe the waves of ECG and put these letters according to alphabetic order from P to T, and P, Q, R, and S, T, all these waves were described by him. By the way, look at the last U wave. It's often is described as well, but really not often it can be seen, and it has no great diagnostic value. So usually, from the beginning I should say that I will not even show this because it's not Really, I didn't see. Of course, I'm not an experienced investigator who on a daily basis can see the ECGs. But while studying in the university and looking into different ECG, I didn't see it, and so I don't think that it's of greatest importance. So, for basically, we consider main P, Q, R, S, and T, and they are named due to suggestions of Einthoven, as well as electrodes placement and many moments of analysis of ECG. So this, again, I'll show you this phase for better remembering of basics of ECG. Maybe it's not of greatest importance, but it's necessary to make respect for the people who worked to develop this, and of course mainly it helps to remember better. So the standard leads of ECG, they were suggested by Einthoven, and they form triangle. First, you should understand what is a lead. Lead is the pair of electrode which records the difference of potential. And basically, ECG is a record of difference of potential. And actually, electrocardiograph device records something like, it's simply like a voltmeter, very complicated. By voltmeter, it measures the difference of potential that constantly changes. And therefore, for measurement of difference, we always need a pair of electrodes. We cannot register difference using one electrode. It's always a pair. But these pairs can be different. If both electrodes in one pair, so they make a lead, both electrodes are equally important and both influence the difference equally, so these electrodes, this lead we call bipolar. The other leads can be called unipolar, not because the electrode is the only one. Electrodes are always in pair, but there is a difference. One electrode is main, and the difference depends mostly or only on this electrode, and the other electrode is additional. So in this case the electrodes are not equal, so we called unipolar leads. But first let's start from the standard bipolar leads, 3 of them suggested early by Einthoven. Look, first electrode is applied to the, actually first, second, it doesn't matter. They are colored in order to not to mix them. Electrode for the right hand has the red color, red electrode. Left hand electrode is colored in yellow, so you don't mix it. Then the left leg electrode is colored in green. And finally, if you remember how it is done, there is one more electrode, not active, but this is the black electrode applied for the right leg for grounding. So it's not active and it's not measured, but it's for grounding. So therefore, for the recording of ECG, we apply the 4 different electrodes, but 3 are for measurements. And so they form between 3, they can form 3 pairs, and exactly they are 3 standard leads. First lead, they usually are designated by the Latin Roman numbers. So number 1 is between 2 hands. Therefore, the axis of this lead passes through the heart directly, exactly horizontally. Then between the right hand and the left leg, the second pair, second standard lead is created, and this shown on the triangle, the second lead. And then the third pair between everything left hand and left leg. This is electrode number 3, lead number 3, sorry. So, and they always are like this. First lead with horizontal axis, then second lead between right hand and left leg, and between left hand and left leg, the standard lead number 3. And then you can observe that all the 3 leads have the axis where the real vector that shows the direction of conduction of excitation from excited to non-excited parts of the heart, this vector is projected according to regular rules of projection perpendicularly. This is general electrical axis of the heart. Of course, during the cardiac cycle, this axis direction can be changed, but generally as a total average axis is directed like this, from the area where excitation appears first, which is sinoatrial or sinus node in the right atrium. The excitation becomes conducted downwards through interventricular septum, finally to the apex. And so general electrical axis of the heart is directed from the right atrium down to apex. And you see, from all the leads, most parallel, not perfectly parallel, but most parallel to this axis is the second lead. So if projection is done to the second lead perpendicularly, it makes certain amplitude of all waves. The same waves projected from the general electrical axis or vector of the heart to the first lead, normally it makes smaller amplitude of waves, and the third lead has the smallest value of the projection of all the waves to the axis of the third lead. So you can see the second lead normally is leading in amplitude, and standardly it's taken that intervals measurement, intervals do not differ in different points, in different leads. Intervals are all measured exactly in this lead 2 with maximal amplitude. Main measurement of waves and especially intervals are made exactly in a standard lead 2. The vertical side can be measured in different, in all of them, but intervals mostly used for measurement lead 2. Let's observe more detailed the triangle of Einthoven for understanding the position of the electrical axis of the heart and its influence on standard lead amplitude at least. look again, we see just enlarged the same picture with first lead axis horizontal. Actually, this axis should pass through the heart, but for a triangle it's easier to observe like this. Again, axis of the second lead and axis of the third lead. Now the general axis vector of the heart excitation. It goes from excited portion down to non-excited, and basically it goes from right atrium down to apex of the heart. And now let's make the same projections to the second lead, to the first, and to the third. And so you see, if the axis is directed like it's shown, it's a normal variant, about 60 degrees, according to up to 60 degrees from the horizontal direction. It's a normal position of the electrical axis of the heart, and in this case maximal amplitude of all waves is characteristic for the lead 2, and basically and for lead 3 minimal amplitude. Basically amplitude is compared between the largest wave of the ECG, which is R wave, the sharp wave directed upward positively in the middle of the whole complex PQRST. So R amplitude first to be compared in different leads, and naturally, as you can see from this triangle, regular this difference goes in such an order: highest amplitude for R wave in the second lead, then less in the first, and then less in the third. So it's approximately 60 degrees to the horizontal value of angle, and then it's a normal position of the heart axis. But heart axis can be changed, direction can be changed due to at least two reasons. First reason can be simply anatomical. The heart position in the chest can be different depending on people's general body structure. Some people tend to have shorter chest and wider, and they tend to have more horizontal position of the heart in the chest cavity, especially with the higher body weight also it may happen. And some people are very thin and tall, and the position of the heart in the chest cavity is more vertical. Corresponding electrical axis also will be directed more vertical. But also there can be different other reasons, like hypertrophy of one part of the heart, right or left. And clearly, if there is a hypertrophy of the left side of the heart, of left ventricle, for example, the total mass of the left ventricle will deviate the axis to the left. And correspondingly, in case of the hypertrophy of the right ventricle, the electrical axis will be shifted also to the right. So it's important to detect the position of the electrical axis. Of course, full estimation of position of electrical axis includes not only standard leads, but we begin the general estimation of ECG, not very deep, so at least this is good enough if you understand this difference. Look, again, this is more vertical position of electrical axis, and immediately it changes the values of projections. As for the second lead projection, amplitude does not become decreased much, but you may see big difference. The first lead amplitude becomes less, while the amplitude in the third lead becomes larger. This darker blue color shows the difference. So for the deviation of the electrical axis to the more vertical position, we have changed the third and first leads amplitude of R wave becomes changed positions. The third becomes higher than in the first lead. It corresponds to the more vertical position of the heart axis. So it simply can be deduced from the Einthoven's triangle. And in opposite case, when the electrical axis of the heart becomes deviated to the more horizontal position, to the left. You see, in this case, it increases the amplitude of waves in the first lead and decreases in the second, and especially decreases in the third. So again, order becomes changed. First and second lead turn their places, and more horizontal position of electrical axis of the heart changes the ratio of amplitudes in different standard bipolar leads of Einthoven. So at least this comparison can help to understand the idea of the electrical axis of the heart. Then, the first three bipolar standard leads, according to Einthoven, are only three, and total number of all leads used for classical analysis of ECG makes 12. So, after the next three are called the augmented unipolar limb leads. As for unipolar, I have already explained that even unipolar limb leads any unipolar leads always involve two electrodes, but these electrodes are not equal in their influence on the difference of potentials, and here they are not equal. Picture still shows classical bipolar leads, but now let's make a different reference that explains, because it's not necessary to apply new additional electrodes for registration of the augmented unipolar limb leads, because electrodes remain the same, just different connection is necessary. Here is a characteristic look of the three unipolar limb leads, augmented ones. And they are called corresponding AVR, AVL, and AVF. It's easy to understand where these letters come from. So main electrode is one of the standard electrodes, and second electrode in this case for augmented unipolar leads is electrode joined from the two other standard lead electrodes. Look, for example, for AVR, R stands for right hand electrode is the main, while the other two from the left leg and from the left hand become joined. So it can be just done within the device that records the electrodes are connected for recording of this, and so the AVR lead can be registered. Then for AVL, left hand electrode, which is the main, is placed on the left hand, and the other two become connected from the right hand and left leg. So this, and finally AVF, left leg, F here for foot, right, R for right, L for left, and F for foot. Electrode, the main one, is on the left leg, foot electrode, and the other two are connected. Notice that axes of these leads are perpendicular, exactly perpendicular to the standard leads. For example, the AVF axis is perpendicular to the two upper electrodes which make horizontal line. Therefore, the AVF axis passes through the heart directly vertically, perpendicular to the first lead, because it combines both electrodes on the two hands. So it goes from foot to direction of these two electrodes to horizontal line and perpendicularly, so it's vertical. By the way, from which these letters go from which source? A stands for augmented, which means increased, and V for voltage, and R for right and corresponding with the rest. Usually it's not mentioned, it's just AVR, AVL, and no one goes into full abbreviations of these words. So now we have 6 different records, 3 standard according to Einthoven and 3 augmented unipolar limb leads. So it's a half of all the leads that are used. And now the chest unipolar leads that are designated by letter V, V1 until V6. They look like the following. For recording of these unipolar leads, the main electrode is placed on the chest surface. And you see on the picture the main electrodes. There are 6 points, black points on the chest surface where the electrodes are correspondingly placed. This electrode is the main, and exactly difference of potential depends on this electrode, while the other electrode is the indifferent that is made by joining of all the 3 standard electrodes. So they are joined here, shown in this area, and finally we measure difference, but on these 3 joined electrodes the potential is constant, because after summation of all them the sum is not changed. So the difference depends exactly on the chest electrode. And as the electrode is located exactly on the chest surface, that each electrode has the axis that passes through the heart through different portions of the heart. And so it shows the state of the this portion of the heart that is located closest to this electrode. And it enables us to detect local abnormalities. Because if there's a rhythm disturbance, the rhythm is changed in all the leads. But if it's something that related to problem in blood supply to the heart, it can be different in different parts of the heart. And so it can be detected by the chest unipolar leads. And to be more exact, let's consider this. But first, the difference between V1 to V6 electrodes. First, the heart projection is somewhere like here, and you can see V1 and V2 electrodes are placed in both sides of the sternum in the fifth intercostal space, and here the heart is turned to these electrodes by its right side, right ventricle predominantly, so and they even are called right chest leads. Then leads 3 and 4 are located above the ventricular septum and apex of the heart, and mostly they consider to be reflecting exactly the state of this part of the heart. And finally, V5 and V6 are located closer to just above the left ventricle, and usually they are called the left chest leads. For more detailed consideration, we'll have the next slide. First, let's observe the application where we put this lead, these electrodes, chest electrodes, for recording the chest leads. Of course, mainly you are going to study this in the propedeutics of internal diseases, but even now it's necessary to have an idea how electrodes are placed. So the first, they go by horizontal line between first and second electrodes, placed in both sides of the sternum, and it's necessary to find the fourth intercostal space, and just to the right side of the sternum the first electrode is placed. Symmetrically in the same intercostal space, the second electrode is placed just to the left side from the sternum. The electrode number 3, usually they say it's placed between second and fourth, and it comes over the rib, and the fourth exactly is placed in the fifth intercostal space on the medial clavicular line. So we go down one intercostal space from 2 to 3 and 4 electrodes. Then electrodes go according to a horizontal line again, regardless of intercostal space. Just number 5 is placed along the anterior axillary line, and number 6 in the medial axillary line. So, and all 4, 5, and 6 are located horizontally, one after another. So, and let's look now how it looks above. This circle shown beneath shows the body cross section, and then we can see how axes pass through the different parts of the heart and come to these electrodes. Look, V1 and V2, which are right leads, really are passing through the right ventricular wall, V1 and V2. Then V3 and V4 pass through the ventricular septum, interventricular septum, and apex. And V5 and V6 pass through the left ventricular wall. So that's why they are called left leads. And you see, the abnormalities, if they are present, can be expressed differently in different parts of the heart. And so in order to detect something like infarction of myocardium or hypoxia problems or some others, we can look at the chest leads in order to determine which part of the heart really suffers from inadequate blood supply. Now, basis of ECG formation. For this purpose, we need to recall the conductive system of the heart. So I simply repeat the slide from the lecture about the heart just to remind you how the excitation goes along the heart. First, excitation appears in the sinus node, the pacemaker of the heart, where the first group of cells, pacemaker cells, become depolarized automatically. Then these cells easily excite the fibers that pass from this node along the walls of the atria down to the next atrioventricular node. And I remind you that conduction goes through atria very quickly, but then in the atrioventricular node, conduction suddenly becomes slowed down so much so that conduction becomes few centimeters per second. And this is atrioventricular delay that allows to finish contraction, not only excitation but contraction of the atria, and then excitation and correspondingly contraction of ventricles may start. Then atrioventricular node sends impulses down the atrioventricular bundle of his, and which passes through fibrous ring, annulus fibrosis through the opening, passes down to the interventricular septum, where bundle of his is divided into right and left branches, and they go beneath endocardium downward to the apex, and then make branches going upward to the basis of the heart, of the ventricular walls. And final Purkinje fibers produce impulses and transportation, conduction down to the contractile muscle cells. And so the velocity of conduction here becomes progressively higher and higher, 2, 3, and finally 4 meters per second in Purkinje fibers. So this is the highest velocity of conduction. But for ECG, it's important to remember that excitation appears in the right atrium, in the sinoatrial node, then goes downwards through interventricular septum to apex. And so the general axis of the heart comes exactly from the right atrium downward to the apex, and only then excitation goes upward. So first we should consider how the ECG record makes the positive or negative waves. It depends on the direction of conduction from excited to unexcited area. And let's consider the first beginning of excitation. And common general axis of the heart passes from the sinus node, excited at the moment, so that inside it becomes positive and surface is negative. And excitation goes to the still not excited, negative inside, resting state of cells, and positivity on the surface. From minus to plus, this axis is directed downward to the apex. This is classical direction of the common axis of the heart. And if we take this common axis, of course, not necessarily the vector of conduction of excitation from excited to non-excited parts of the heart constantly changes within the cardiac cycle during the conduction of the excitation. But all the directions that are located from this perpendicular line, they located downward, so any direction like this. Direction which projection finally goes to the same side as the axis of the heart. If projection comes to this side, so it creates the positive difference of potentials according to mechanism of application of electrodes and recording. And so it creates on the electronegative line deflection, deviation of record to upward to the positive side. So this creates a positive wave. But when vector of conduction through the heart from excited to non-excited area is directed any direction that comes to the opposite side to the perpendicular, and projection goes anyway oppositely, so in this case it creates the opposite deviation of the record downward, which is negative. So this is a mechanism of formation of positive and negative waves of the ECG. And now we can consider in general details how the waves are formed. It corresponds to the sequence of the heart excitation. Let's first see the atrial excitation, which is the beginning process. And before atria start to be excited, all the heart muscle is equally non-excited and there is no difference of potential. So remember, we detect not potentials themselves, not absolute values. We detect difference of potential and record this difference. So when sinus node begins its automatic excitation, first there appears the little difference. This group of cells in the sinoatrial node is already excited and the other are not excited. So, and there appears small, at first small difference of potentials. And vector is directed from sinus node to all the parts of atria. But if you combine all the vectors directed downward, directed to the left side, all together they finally form vector that generally goes, at least its projection goes down the common axis of the heart. So it creates positive vector corresponding to the axis, and it creates the positive deviation of the potential from zero, from absence of difference. Positive difference of potentials is registered. Gradually, when progressively more and more cells in the atria become excited, the potential difference reaches the highest level for this activation, excitation of atria. Approximately when half cells excited, half not. So in this case it reaches maximal, and then when excited cells start to predominate, this difference decreases until the moment when totally all atria become excited. And then there is no difference between atria and their potential. Everything is excited. So it looks like it produces first wave of ECG, which is designated by P letter, and this moment of the end of P corresponds to the picture that shows complete excitation of atria. Complete. And then you remember that atrioventricular node does not start immediately to conduct this impulse, and there is atrioventricular delay. And so excitation of atria is already done and it lasts, and excitation of ventricles doesn't start. So the difference of potential still is absent. No potential difference, and line makes straight line along the neutron. Then finally atrioventricular node starts to conduct impulses downward to ventricles, and the whole sequence of excitation of ventricles occurs. So ventricular excitation produces the complex, not only one wave but few waves fused together, and we name this the complex of QRS. The wave Q sometimes can be absent, but in many cases it's present. QRS is a total sequence of waves that characterizes the process of conduction through ventricles. Now we switch to next. This is already explained, P wave, and we come to explanation of QRS waves genesis. So here you see the picture down that begins excitation of ventricles, and through atrioventricular bundle of his, impulses are sent downward through its branches to the apex. And when it goes to the apex, at first, in many people there appears little moment when the left ventricular part, left part of interventricular septum becomes excited earlier than right. Therefore, if direction of conduction for a short time just turns from already excited left portion of the interventricular septum upper part to the right interventricular septum portion, this creates the arrow, the vector like the picture shows, which is directed to opposite direction, which at least projection goes oppositely to the common axis of the heart. And so for a short moment there appears the negative deviation of the record to the negative side. But very soon this right portion of the upper interventricular septum becomes excited as well, and then general vector goes according to the common axis of the heart through the interventricular septum down to the apex of the heart, and it creates great upstroke of the potential difference, and it goes to the positive side, and it forms the ascending portion of the R wave. Then it reaches the bottom, the apex, and now vector goes, excitation is passed up the walls of the heart, so the vector becomes opposite, and again difference of potential turns to be negative at the moment because projection goes to the opposite side, and it creates descending portion. But then very soon excitation is almost over. At first it reaches from inner sides, it becomes spread to the outer surface of the myocardium, and then finally we can see that totally all the heart becomes excited, all the ventricles, and it looks like this. The yellow color shows now excitation of totally all ventricles, and then it means that there is no difference of potentials again, and so the time goes. Ventricles become excited for a certain time. You remember the potential, from potential that lasts about 300 milliseconds, so it takes time. Excitation is conducted, then it takes all the ventricles and it keeps ventricles excited and contracted. And during this time there is no difference of potential, and therefore line goes along the electroneutral line, zero difference of potentials. And then after then you remember that calcium channels become closed and repolarization is quick. Quick repolarization begins not from the areas that become depolarized earlier, but from the last depolarized surface. So the picture of repolarization actually looks like the picture to the left side from the complete excitation. Excitation reaches the surface and then goes out from surface, and so superficial area becomes already repolarized and inner part is depolarized. So direction of vector remains the same, positive, as during conduction of excitation, and therefore the single wave that corresponds to the repolarization, wave T, is positive in normal conditions, of course. So you see, finally we have the 5 classical waves of the ECG. P, which shows how excitation goes through atria, then complex QRS. All these three waves show the process of excitation conduction through ventricles. In some people Q wave can be absent, and even S can be absent, but mostly it's present. Q wave can be absent, and so immediately R and S appear. And T wave shows the process of repolarization of ventricles. You may notice that there is no repolarization of atria. In many textbooks they say that repolarization of atria is masked, covered by QRS complex. But in reality, even when block happens between atria and ventricles do not get this impulse, and there is simply electroneutral line after P, there is no signs of repolarization of atria. Perhaps they go in such a way that individual vectors of each dipole of each myocardial fiber creates differently directed vectors that together summated produce practically zero. So it's very negligible if it can be present, but naturally it's not present on ECG. It doesn't matter masked by QRS or not. So let's now observe the intervals and waves of the standard lead 2 for ECG. These waves are intervals you should know well. First, before observation of the ECG record, you should know that there should be standardly recorded, because we can amplify very weak impulses, just a few millivolt. We can amplify stronger or weaker, and it will look differently, but we should be able to compare, to make standard way of recording. And standard for vertical size for voltage is provided by calibration. It makes signal of 1 millivolt always go upward, make amplitude of 10 millimeters. And in the beginning of each record there should be this calibration signal. It should look like the following. This is calibration signal. When signal 1 millivolt comes to the record goes upward and shows amplitude normally exactly 10 millimeters. Otherwise it can be adjusted so that it makes perfectly 10 millimeters. So in this case it's standard record, and it can be compared in voltage in millivolts of amplitude. Also, calibration for the horizontal line is the standard velocity of record. Classically, here in Minsk we record at velocity 50 millimeters per second, but in many textbooks they say that they use 25 millimeters, so it's slower movement of the record, and so in each piece of record contains more waves. But anyway, it's recalculated in time, therefore values received after analysis of both types of record are not entirely different. They are exactly the same, because just the value of each portion of paper is, or record, is recalculated. So this is the first wave, P wave, and if you remember, it corresponds to the depolarization of atria. Actually, you may say not only depolarization, you may say excitation of atria, excitation conduction through atria. But depolarization is preferential, because when you say depolarization, you easily find the word for the T wave, repolarization. But if you say excitation, you will not easily find the opposite word for T wave. But repolarization is clearly opposite to depolarization. So, atrial depolarization, P. Also, we measure, after P, there is the part of the isoelectric line, and together P and this isoelectric line portion make the classical interval that is called PR or PQ. Why it's so important, this interval? Beginning of P, this first point of the red color, is the beginning of excitation of atrium. The end of this red line, where the Q wave begins, it's the beginning of excitation of ventricles. And horizontal direction shows the time. So if we measure this interval, this is exactly time of conduction of impulse or excitation from atria to ventricles. This is important. With velocity of 50 millimeters per second classical, 1 millimeter is 1/50th portion, or 200 of a second, 0.02 second. And so, if it's measured in millimeters first, then it can be multiplied by 0.02, and you get value of time in second. Norm of this time is 0.12 up to 0.20 of a second. So, up to 5th portion of a second, it should take conduction from atria to ventricles. If it's higher, it shows that there is a problem of atrioventricular conduction. And general term which is used for this abnormality is the atrioventricular block. But in future you're going to study pathological physiology, where a detailed consideration of types of block are considered. And they consider first the degree of block when this PQ or PR interval is just prolonged constantly without any big consequences. Then the higher degree when sometimes after P wave conduction becomes worse, PR, PQ interval becomes longer, and finally there is no conduction at all, and there is a missed QRS complex, no excitation of ventricles. Then it starts again, PQ interval more or less normal or elevated, then longer, and stop conduction, and QRS complex disappears. And there is a full block, complete block of between atria and ventricles, where when excitation of atria does not produce excitation in ventricles, and ventricles become excited due to atrioventricular node or other parts of the conductive system which produce less rate of impulses, and ventricles follow this less rate by less contractions, and there is no any connection between atrial activity and ventricular, and therefore P waves come independently of QRS wave. Or actually it's better to say that QRS waves appear independently of P wave after regular intervals, but these intervals are longer between RR than intervals between P and next P. But now let's consider it a norm. So again, PQ interval is called, but also can be called PR because Q wave sometimes can be absent. So 0.12 minimally, 0.20 maximally. This is normal interval of conduction between atria and ventricles. Then comes QRS complex. And also it should take some limited time because it's a conduction through ventricular conductive system to the heart, and it should be no longer than normal. And normal is QRS complex that shows depolarization of ventricles. Normally is from 0.06 up to 0.1 or 10 of second. Actually, if you want to memorize easily, you can notice that both values, lower and upper limit, is exactly 2 times less than for PQ interval. 12 and 6, 20 and 10. So maximally up to 0.10, while PQ maximally 0.2. Then comes the isoelectric line that should be located always on the isoelectric line level, so that there is no any additional current, because in case of damage of the heart, in case of hypoxia, this piece of ECG, which is called not the wave but ST segment, there is no wave, and it's only portion between S and T waves, ST segment, and should be always located on the isoelectric line. Maximal deviation, which is still within norm, is 1 millimeter, and doesn't matter upward from the isoelectric line or downward. No more than 1 millimeter is allowed. Any further difference from isoelectric line makes us able to say that there is a hypoxia and insufficiency. Actually, we mostly say ischemia. Ischemia means exactly insufficient blood supply. The heart ischemia. And ischemia is accompanied by hypoxia, of course. So this is ST segment. Then final T wave represents repolarization of ventricles. Again, let's recall. For ventricles, we have QRS complex of 3 or sometimes less waves that represent the depolarization or excitation, and we have repolarization T wave. And for atria, we have only wave that shows depolarization or excitation, which is P wave. Also, for normal ECG, usually isoelectric line is between T and next cycle P. But in some cases, there is a damage of the heart which produces current and difference of potential, which is present even at rest abnormally. And isoelectric line between T and P is already not really isoelectric. It shows the presence of this pathological current. And for this case, we may use specific point to determine the real isoelectric point, and it corresponds to the moment when excitation of ventricles is finished. And excitation of ventricles is represented by QRS complex. So the point when QRS complex is over and S wave is ended, or generally complex is ended, it's this point. It's called G point. So exactly this point when QRS complex is finished shows exactly absence of any currents, any difference in potential between parts of the ventricles. So this is the reference point to find the negative isoelectric line. Then heart rate calculation from ECG. It's an easy process, but for many cases I have experienced that it can be a problem. So let's consider this. This is a sample with millimeter paper. So how you operate? First, you should assess calibration, of course, it's according to rules, but it's perfectly 10 millimeter normal. It's a second lead for analysis, and each millivolt equals to 10 millimeter, it's correct. And velocity of movement of paper is 50 millimeters per second. It's usually indicated always. Measurement of the heart rate is based on estimation of the duration of each cardiac cycle. And the best way of finding the cardiac cycle duration is measurement of the RR interval. These are sharpest waves, easily found, easily measured distance between them, and it represents the duration of cardiac cycle. Of course, to find true RR, we should measure at least 5 intervals and find the average mean value, because they are not equal even in normal case. They should be slightly different, for the rhythmical excitation. So, and it's 1 cardiac cycle, and then you should convert millimeters into time in seconds, and each millimeter makes 0.02 seconds. In case of movement of record, 50 millimeters per second. And then, if you don't remember the equation, the way to calculate, and it's very easy to deduce the formula yourself. Just its classical proportion. One side should be contractions, another side time, and don't mix, change the position of these points. One contraction, which is one cardiac cycle, corresponds to the duration of RR interval. But you want to find number of contraction unknown at the moment, which will take 60 seconds in time. So X is exactly our heart rate, which we need to find. And proportion is like this, 60 multiplied by 1 and divided by RR. But simply it means that heart rate is calculated as 60 divided by duration of RR interval in seconds. 60 seconds you divide by number of points of fraction of second for each contraction. So it's an easy thing, but if you memorize mechanically, many students do it. They multiply by 60, they divide by 60, they do anything but not correct. So if you understand the way of calculation, you always can do it easily. And so in this case in particular, look, calculation of the RR interval. It's not necessary to count each millimeter individually, 10, 10, 10, and some more, 4 in this case. So total duration makes 34 millimeters. So 34 millimeters by 0.02 makes 0.68 seconds. This is one cardiac cycle. And heart rate is 60 divided by duration of single cardiac cycle. And for this case calculation, we get heart rate 88 contractions or beats per minute. And for any other way, we can just change the values and calculate easily. Then, examples of atrioventricular blocks. Just show you how impaired conduction can change ECG. And ECG, in this case, it's very good way for diagnostic, very good tool. Of course, the schematical presentation is not true ECG, but it's easy to see that here it's normal ECG. It looks like record done with velocity 25 millimeters per second. So everything becomes packed tightly, but it's for reference, normal. Then look, next, partial atrioventricular block. Every second impulse is not conducted, you see? Here P wave is present, but there is no QRS. Again, P wave, no QRS. So it's changes. One impulse is conducted and the second impulse is not conducted, and so it goes like this. Clearly, number of contractions of the heart corresponds to the number of the QRS complexes, because ventricular contractions exactly provide pumping function, so the heart rate will be decreased. And lower line represents the complete AV block. Atria and ventricles have excitation independent. Look, P waves come in a regular fashion with normal frequency as corresponds to the upper normal ECG. But QRS waves do not appear just after P wave. For example, in the second complex, you can see that P wave really appears before, but it's too much before, and QRS complex is not related to this P. Next time QRS appears when P wave was long ago, and QRS is not related to excitation of atria. Ventricles become excited due to their own rhythm, which is lower frequency of impulses, and so QRS complexes appear with its own rhythmical excitation with clearly much less frequency, and heart rate is low. It's a complete atrioventricular block when full independence of ventricles from the atrium. Then pulse wave, just to remind you about sphegogram, because we considered this before, and you can see here that classical sphygmogram record consists of the ascending part, which is anacrota, then it reaches maximal point shown by red arrow. Then there is a decrease, which is called the descending portion is called the catacrota, and on this catacrota we have incisure and decrotic notch. And decrotic notch appears due to reflection of blood, which tried to move back into ventricles and filled the valves. And the aortic valve filled, and this blood then cannot go back to ventricle because valves are closed, and then it moves along the aorta again and produces little additional dilation of the aorta. So this is a decrotic notch. And now we come to the heart sounds. Let's consider. Classically, there are 4 heart sounds, but in most cases we have just 2. And the third and fourth may appear mainly in children or younger people. So first heart sounds occurs due to closure of atrioventricular valves. And when they close, they produce oscillation of the heart as a whole, and the heart walls also involved into formation of this sound. And main component comes from the atrioventricular valves closure. So as this process occurs in the beginning of the systole, so clearly it shows the beginning of systole, and this is systolic heart sound. By the way, even if there is no difference in sounds themselves, in the duration, in their pitch, their frequency, even if they come after equal periods between first and second and first, we always can differentiate first sound from others because it's systolic, and it always almost coincides with the heartbeat, and more or less coincides with the pulse wave propagation through large arteries. The second heart sound is produced by oscillations due to closure of semilunar valves. Semilunar valves close really with snap, clear heard sound, and it produces vibration of the structures around the aorta itself, and they correspondingly will be well conducted to the chest in the area where these vessels pass, basically aorta and also pulmonary artery. And as this process of closure of semilunar valves occurs in the beginning of diastole, clearly the heart sound will occur during diastolic. Then, if there are 2 more heart sounds, even if you don't remember why they are developed, why? You can, on the basis of knowledge of the cardiac cycle, you can deduce yourself. After the closure of semilunar valves, next event will be opening of atrioventricular and beginning of filling of the heart, of ventricles. So after this, which periods we observe? The rapid ventricular filling, then reduced ventricular filling, and finally the filling due to atrial contraction. 3 events occur later. And then again we start systole and first heart sound comes. So these 3 events should produce 2 sounds, the third and fourth, in case they are present. So, and it's easy to choose which of 3 events can produce more probably sound, rapid or reduced filling. Clearly, rapid filling is much more probable to produce sound. So the heart sound number 3 occurs if it occurs during rapid ventricular filling, which comes very soon after the second heart sound, because isovolumetric relaxation phase is very short, and second heart sound begins with the beginning of this phase and ends almost by the end. And very soon the pressure drops so that atrioventricular valves become open and rapid ventricular filling begins. And exactly this rapid ventricular filling produces the third sound, for example, in young children. Then the fourth sound, again, what is more probable to produce one more sound? Reduced filling or atrial contraction with additional filling of the heart. Exactly the oscillation of the ventricular wall due to filling, active filling by atrial systole. I hope you understand that systole itself, atrial or ventricular contraction of the muscle cells, do not produce any sound. This all comes from oscillation, vibration of ventricular walls or arterial walls in case of second heart sound. So there are 4 sounds. In most cases, the third and fourth are not heard. Timing of heart sounds should be estimated, of course, in parallel with registration of ECG. And you should be able to draw both ECG not separately from in phonocardiogram, but together, in parallel, in synchronous registering. And for this correct recording, correct drawing of the picture, you should remember that there is reason and consequence. Reasons, excitation produces mechanical events, contraction and closure of valves, which results in sounds. So event on ECG should appear earlier, excitation of certain part of the heart, then contraction goes slightly later, and this contraction produces closure of valves. For example, and mostly of course for first and second heart sounds. You see, first heart sound comes due to closure of AV valves, which occurs in the beginning of systole. Systole appears after excitation beginning in ventricles. Ventricular excitation begins with the first point of Q wave. Here, this is the moment where excitation in ventricles just begins, and clearly at the same time it's not it's too early to expect that the heart ventricles will contract. They just start to be excited, and slightly later contraction comes, and contraction causes closure of AV valves and sound. So excitation begins, and later ventricular contraction and first heart sound both follow. So this is first heart sound, and you see this blue line shows that little time difference between Q and beginning of Q and first heart sound, and this period can be measured. And if you remember that there is a period Q first sound, so we always will put first sound after. Then for the second heart sound occurs when ventricles begin relaxation, and relaxation produces backflow of the heart that fills the valve and closes aortic valve. So in this case we should wait until repolarization is over, because until repolarization finishes, that relaxation doesn't occur. End of depolarization. Here this line just shows you again that similarly Q first sound period appears in the next cycle. But let's come back to the second heart sound. This is the end of repolarization. So at this moment ventricles begin their relaxation approximately, and just slightly later relaxation brings the closure of semilunar valves. So between the end of T and second heart sound also there is a little period of time, little interval, there are little few hundredths of a second. So T second sound, but note the difference. Q first sound means beginning of Q point and beginning of first sound, but the interval between T and second sound means the end of T and beginning of the second sound. Both intervals are very little. Then when you draw the picture, you can draw very soon the third sound after the second one, but it doesn't is not related to any event on the ECG, because it corresponds to the electronegative isoelectric line. Then it occurs during passive diastolic filling, in particular during rapid diastolic filling. And then the fourth heart sound should be located relative to ECG correctly, because it results from contraction of atria. Contraction of atria never starts simultaneously or even earlier before excitation. This is the moment of beginning of excitation, beginning of P. So excitation starts and contraction comes later, and this contraction produces the fourth sound if it's present. So fourth sound occurs usually somewhere in the end of P wave, closer to the end of P wave. So this is a timing of the four heart sound corresponding to ECG, and it's logical. Excitation always precedes the contraction and sounds, and main component of the sounds related to closure of valves always should be later than excitation. And now the heart murmurs. Generally we consider normal physiology, but different abnormal sounds that can appear in the heart are closely related to functioning of the heart and to cardiac cycle, and so we can understand easily on the basis of information we can understand the murmur's appearance. What is the murmur? It appears when blood passes through too much narrowed openings and under too high pressure. Both factors are important. Normally, the openings are enough for blood to pass without great sounds, and only sounds which we considered by now normal sounds can be present. But if pressure is too high and or BOS present, narrow opening and increased pressure, the heart produces other sounds which are noises, or normally they are called murmurs. And usually the main reasons are valvular defects, defects of the valves. There are two major types of valvular defects. It can be narrowed opening, so when the valve is open, it's not open enough. It's called stenosis. And the opposite case, insufficiency of valves closure. It means that valves cusps do not become tightly closed and there appears the opening still. And this results in regurgitation, which means backflow. So now let's recall again. We have aortic valve, pulmonary artery valve, both are semilunar. Then we have mitral valve in the left side of the heart and tricuspid valve between atrium and ventricle in the right side. So they are atrioventricular valves. And valves abnormalities sometimes can be congenital, so it requires the surgery from early age. But mostly they come from inflammatory processes, mostly due to rheumatic heart disease, when endocardium is inflamed and then develops the fibrosis. And fibrous tissue develops in the endocardium especially. It can produce both stenosis and insufficiency. When mostly it refers to the opening, it may cause not elastic tissue that shortens the opening and makes it smaller. It's predominant stenosis. But also the inflammation mostly can affect the cusps of valves so that they cannot be closed enough, and there appears the opening between them, because the scar tissue, fibrous tissue, makes it smaller, shorter and less elastic. So usually one of these two changes predominate, and not often they become combined. Both types are present simultaneously. Mostly something predominates. Let's observe what happens in case of both stenosis and insufficiency for different types of valves. The most typical heart murmurs. First, in this picture, you should observe the upper portion where you see regular sounds of the heart. This is how to understand which murmur is systolic and which is diastolic. The normal heart sounds are points where you can easily find. First heart sound appears in the beginning of systole, so here between first and second sounds there is a systole piece, systole time. And between the second and the next cycle, first heart sound, there is a diastole. So it's easy to find the murmur is diastolic or systolic. If it's between first and second sounds, it's systolic. If between second and first, it's the diastolic. And let's consider which murmurs are characteristic for different types of abnormality. First, we consider systolic murmurs. Systolic murmurs appear during systole. So here you see the picture where the ventricles are in the contracted state. Ventricles contract and normally should push blood through aorta and pulmonary artery. And so these valves should be well open for both pulmonary artery and aorta. And you see the decreased size of the ventricle shows the contraction period. For left ventricle, it's high pressure developing ventricle and pushes the blood into aorta. And just imagine if aortic opening is narrowed. This green circle shows great narrowing of aorta, and then during ejection period, blood will move. Not usually, it's even under normal conditions, it's more or less turbulent blood flow, but now is narrowed, it will be greatly turbulent. And it produces the strongest and loudest heart murmur, because left ventricle produces highest possible pressure in the whole, among all the chambers of the heart. And you see, this is great amplitude murmur, murmur which is systolic, and very loudly goes within the whole systole, especially in the most part, 2/3 at least. Very loud. They say that in severe cases it can be heard without any stethoscope, without even close location to the patient, it could from meter or from 2 meters, standing from patient, we can hear the great noise, at least it's audible, when each systole occurs in the patient with severe aortic stenosis, because blood is hardly pushed through the narrowed aorta. So this is systolic. But another case of the systolic murmur may occur in case of, look, mitral regurgitation. It means that mitral valve is not sufficiently closed. Here now, if you look at the mitral valve area, you can see here I placed opening. It should be closed tightly during systole, but the cusps are suffered due to inflammatory process, now replaced by fibrous tissue, and this fibrous tissue doesn't provide full tight closure. And during ejection, blood not only goes to the aorta, but also partially goes back to the left atrium. It produces not as loud sound murmur as aortic stenosis, but also it's a systolic. And you see, this little murmur goes through the whole systole. It shows the regurgitation. So we may conclude the aortic stenosis and opposite case of problem with valve mitral regurgitation, both are responsible for systolic murmurs. And they bring the systolic murmurs as well as the pulmonary artery for the right side of the heart, stenosis and tricuspid valve regurgitations easily. So these are reasons of the systolic murmur, and it's easy to understand. During systole, ventricles contract and blood not easily goes through normal exit into aorta, for example, or abnormally goes back and produces regurgitation through not fully closed other valve, atrium and ventricular. Now let's consider the most typical diastolic murmurs. Diastole and murmur will be located between the second heart sound and next again first. So here you see relaxed state of ventricle, which corresponds to diastole. And during diastole, normally blood should easily go from atria to ventricles, so that mitral valve and tricuspid valve should be widely open. And at the same time, blood should not come back from aorta and pulmonary artery, so similar valves should be tightly closed. And if one of these two conditions is affected, so it may produce typical diastolic heart murmurs. Look, these valves should be open, but these valves should be closed. And now let's imagine that aortic valve is not fully closed. Aortic regurgitation occurs. This moment, blood should not come back from aorta, but with opening available, it starts to go because ventricles are relaxed and aorta has high pressure. And so, from a high pressure aorta, blood easily will move back to the relaxed ventricle with low pressure. So aortic regurgitation, as you can see, produces the murmur throughout the whole diastole. Especially high from the beginning, and then with decline of pressure in the aorta, it starts to be less, but it's still present. And the opposite case, stenosis, not regurgitation, but stenosis. For example, in mitral stenosis, very narrow opening between left atrium and left ventricle. Now when blood should passively move downward down to the ventricle from atrium, just the whole accumulated blood during the systole. It should easily move down to ventricle, but with narrow opening, it cannot do it easily, and so it creates this sound during movement, which normally is absent. And this is not very great murmur, but it's present during diastole, and this is the mitral stenosis. So you can conclude now that aortic regurgitation causes backflow during diastole, so diastolic murmur will occur. And mitral stenosis as well produces a problem during diastole. So they both result in the diastolic murmurs. And correspondingly, you may understand that pulmonary artery regurgitation and tricuspid valve stenosis will produce similarly diastolic murmurs. If you understand it, you will never need to mechanically memorize it. And then we come to the final type of investigation for the heart, which is very well helping to the doctors and gives a lot of information. This is ultrasound heart investigations, or also it's called echocardiography. I hope you have an experience in this, and partially you should study in physics this process. Generally, the principle is emitting of ultrasound waves from the receiver, from sensor, and then receiving back reflected ultrasound waves. And direction of the location of the sensor is controlled by a doctor. Then you see the heart outlines are shown, and also you can observe the electrodes, because normal heart ultrasound investigation requires in parallel registration of ECG for comparison of timing different problems. So generally ultrasound is based on different reflection of the ultrasound waves from structures of different density. For example, dense walls of the heart, interventricular septum, reflect back ultrasound waves, while blood that fills the chambers of the heart does not much, so it looks at simply dark black area. And lighter area show the cross section. The most complex moment in this that you don't see three-dimensional view. You see the cross section as rays of ultrasound pass through the heart. They produce cross section view, and can be understood and analyzed with certain experience. And due to this method, we can measure the volume of chambers of the heart. Of course, it's through recalculation. Then we can observe the valves, their opening, their closure, their movement, and degree of their opening and closure. We can estimate the thickness of the walls of the heart, thickness of the interventricular septum. Then we can find defects if they are present somewhere in the septum or somewhere else. Diameter of vessels we can establish, and so on. And with additional Doppler method, which measures the velocity of movement of blood inside, and direction of movement is estimated as well. Also the blood flow can be measured as well. Few moments about view of heart on echocardiogram. Here it's just the schematic presentation. You see that cross section goes through the left ventricle, and also you can see in the cross section aorta with closed at the moment valves, and you can see mitral valve with its two cusps, bicuspid and two cusps, I can see. And now it's replaced by the view like it can be visible in the echocardiograph. Here in the cross section you can observe the following parts. Here is the chamber of the left ventricle filled with blood, so blood makes it dark. Then here you can see portion of the right ventricle, it can be seen in the cross section. Between them there is an interventricular septum. Then you can see left atrium and also aorta above, going out from the left ventricle. And also we can observe here both valves on the left side of the heart. Aortic valve closed at the moment, and mitral valve open at the moment with two cusps. So you may conclude that the moment when it stops, is the whole picture is the moment of the diastole, when filling of ventricle occurs. From left atrium, blood flows into left ventricle, and aortic valve is closed. Also, we can change the cross-section plane, and if it goes through vertical axis, you can see now, you see the heart is upside down. You see the apex is located above and the atria located beneath. You can observe it on the scheme to the right. And here cross-section passes through all four chambers of the heart, and it passes through valves closed at the moment. Look, this is left atrium, this is left ventricle. Between them, bicuspid or mitral valve is closed. Similarly, right ventricle and right atrium and tricuspid valve is closed between them. So you may conclude this is a moment of the systole. So that blood moves not back, but it should move to aorta and pulmonary artery. So mitral valve to the right side, in the left side of the heart, on the right side of the picture, and tricuspid valve in the right side of the heart can be observed. Of course, it's not full idea about echocardiogram, but at least some basics you can understand, and you see that you will not see perfect view, you will see the cross section. So this is the end of our lecture, and thank you for attention. I hope that ECG is interesting, and further you will study more and more about it in the internal diseases, and interpretation of different pathological changes will be studied as well.